right, getting into our final section of Chapter 8. This is 8.5. We are now going to be looking at those conic sections that we've been learning about. We are now going to be able to see how we can use the eccentricity to write these guys into a polar form of their equation. And so we're kind of putting together some new stuff with the old stuff. But I want to take you through a couple of these like boxes and paragraphs of important information at the beginning of this section that we often don't read, but I think it'll be really helpful for this section to help you understand what all is going on here. So the first thing I wanted to talk about is the idea of eccentricity and how it plays into the three conic sections that we've been looking at. So they kind of go back to the initial definition of a conic section, which is they're talking about the set of all points in a plane whose, and this is kind of the key, the distances from the focus in relationship to their distance from the directrix. Now, we've been talking about a focus and a directrix this chapter, and so we're going to look at that on a diagram here in a second, but it's talking about their relationship, right? So basically how the distance that the graph is from its focus and from its directrix and what that relationship looks like. So let me go to this diagram right here. So one of the things that we started out this whole chapter with in the very first lesson when we were looking at parabolas is we talked about in a parabola. So if I were to take a point on this graph, if this were to be a parabola, then the distance from this point to the focus would equal the distance from this point to the directrix. So if these two things are equal, in other words, if the relationship or if the ratio is 1 to 1, then we know it's a parabola. If it's not 1 to 1, then it's not a parabola. We have some other shape, which would either be the ellipse or the hyperbola. And so that's where I wanted to kind of point you down to this box right here at the bottom of page 604 that kind of lays it all out for you. So in the middle, this is the one I was just talking about. So, and this is where we started the chapter. So if it was a parabola, my eccentricity was 1 because, remember how we find eccentricity? It's C over A. So the distance to your focus and the distance to our directrix is what we're looking at right here. So that's what they're talking about on this. And so if those numbers are equal, then it must be a parabola, right? That was one of the main things in a parabola that we started out this chapter with. If they're not equal, then it's one of the other two shapes. And so here's the relationship. So if this distance is greater than this one, so in other words, if it is farther from the focus than it is to the directrix, it must be a hyperbola, right? Because the eccentricity would be greater than 1 if this number is bigger than this number. If it's flipped, if the top number is smaller than the bottom number, right, then it must be an ellipse. The eccentricity would be less than 1, that relationship or that ratio. So in other words, it would be closer to the focus and farther from the directrix is what we'd be looking at right there. Okay, and so that's what this is a really important chart, because the first thing that we have to figure out is what shape am I looking at, right? And this is how you're going to determine that, is by looking at the eccentricity. If you go to the next page, it starts talking about putting these into polar form, and it really lays out where these formulas came from. I'm not going to go through all the ins and outs of how they derive these formulas. You're welcome to read through more of that if you want. One of the things I wanted to point out, though, is one of the major factors in this formula is the K value. And so understand in here that K is the relationship of the directrix. So we get whatever this number is, wherever the directrix is, how far it is from our graph is going to help us determine that K value, right? And so that's one of the things we'll look at when we go through our first example. We'll talk more about that. Down here at the bottom of this page, these are the same 3 items that we were just looking at from the previous page on how do we know what shape it is. So again, I really like these diagrams because it gives you a good visual of how we determine which shape we are looking at. So if this is my focus and this is my directrix, you can see the point on the graph on this one is closer to the focus than it is to the directrix. And so when that happens, we know we're looking at the ellipse. When it is farther from the focus than the directrix, then we're going to, I was thinking about this one. When it's farther, this is a more obvious picture. When it's farther from the focus than it is to the directrix, then we know we have the hyperbola, and that's where you're going to get the eccentricity that's greater than 1. And then this takes us back to the first lesson of this chapter. We looked at something just like this. When this relationship is equal to this one, then we know we have the parabola. One thing to note on this is with a parabola, you only have one focus and one directrix, right? And that's what has a lot to do with these guys being equal to each other. With a ellipse and a hyperbola, you're looking at multiple pairs on this stuff. So they're only showing you one pair, but the same information exists on this side too, right? Because remember, there's another focus point right here, which means there's another directrix right here. And so you're looking at multiple pairs because there's this off-center relationship. And the same thing exists with a hyperbola, right? There's a focus here. There's also a focus here. And that same relationship would exist right here. All right, let me take you to the formulas. The formulas, at first glance, look a little ugly. They're really not that bad. So here's something I want you to keep in mind. These 4 formulas are so similar with just very minor differences. So here's kind of what I wanted you to see on this page. But these are the 4 formulas that we need to be looking at for today. So when you get a problem, the first thing we have to determine is, okay, what shape is it? Well, we're going to determine that by the eccentricity, right? That's what we just looked at on the previous page. So once we determine what shape it is, then we can also determine which formula I should be looking at. And all of that is going to be based on the directrix. So if your directrix is vertical, in other words, your directrix is x equals a number, whether it's on the positive side or it's on the negative side, when it's x equals a number, then we know we're looking at something that is opening left and right. And so if your graph is opening left or right, we're going to have the cosine involved. Remember, cosine relates to your x's. It relates to things that go left and right. But if you look at these two, these guys open up and down, so naturally we're going to be looking at the sine function if it opens up or down. And so that's when your directrix is y equals a number. Because if my directrix is y equals, then I know it's a horizontal line, and that's what's going to cause my graph to open up or down. So remember, your graph always goes away from the directrix. It always goes away from it because my graph is always in between the directrix and the focus, right? So my graph always opens toward the focus and away from the directrix. All that being said, now let's go through some examples. I think these, hopefully that will help give you some good background on what's taking place within these problems right now. So here's the first one they gave us. They said the eccentricity is 0.6, directrix is x equals 3. Well, right off the bat, we know that this is going to be an ellipse because my eccentricity is less than 1. So that's what we just looked at on page, we started with page 604. Right, so we know this is an ellipse, so we can identify that right off the bat. The second thing would be to determine which formula to look at. Because this is x equals 3, I know that this is a vertical line. And if these graphs have a focus at the pole, that's like saying your focus is at 0, 0. Right? At the pole means 0, 0. So if it's at 0, 0, and my directrix is to the right of that, at x equals 3, then my graph must be opening to the left. And that's why they picked this formula that says 1 plus e cosine theta. If your graph opens to the right, as you saw on that book page that we were just looking at, then it's going to be 1 minus e cosine theta. So whether this is a plus or a minus determines whether you're going left or right. From there, you're just plugging in the numbers. Right? And so the eccentricity was given. They plugged in the 0.6 for that. Our K value, remember I told you that is directly related to your directrix. No pun intended. Remember the directrix, we read this as x equals K. And so that's my K value is 3. So that's where he came from. So we just plug in the numbers. And they did a little simplifying on this. All right, so if we do a little cleanup on that, Now, one thing they did on this, which I thought was a little interesting, is if you look at the change from here to here, what they did was they said, let's multiply by 5 over 5 in order to basically get rid of the decimals, right? So if I were to multiply the top by 5 and distribute the 5 to those guys, I'm going to get this look right here, right? And so they took that extra step to get some cleaner numbers so that they weren't working with decimals. I don't know how necessary that would be. I didn't see really explanation on that, but that's what they did in order to clean up the numbers a little bit. Let me show you how you can graph this on a graphing tool. At least I'm going to show you with a graphing calculator. If you're going to use Desmos or something else, you might have to look at how that would play out with a different tool. But I'm going to show you how you could do this with a graphing calculator. So all I did was I followed their directions that they showed right here on page 605, and I made my settings follow after their settings. So it's kind of weird. We're not going to be doing a ton of this. I just wanted to show you. It's kind of neat, but we really have other ways of graphing these things. So what I did was they say go into mode, and they said make sure you're in radians, make sure you're in polar form, and make sure you're in dot form. And so I don't know the difference between dot thick and dot thin. I'm sure this is just a thicker line, and that's a smaller, thinner line. So I just picked dot thick. So those were like the three things they said to put your mode into. They said the window settings were supposed to look like this. So I literally just put in the same window settings that they said to put into here. I'm sure if this was like any other graph, I'd really have to play with these numbers to figure out a good scenario. I mean, the one thing that made sense was they said, let's let theta go from 0 to 2 pi. Okay, that's probably general for all of these. This was just a value they said to put in. As far as your left and right and bottom to top, those could certainly be adjusted pretty easily to fit a decent window. So with your calculator in the right mode, when you go to y equals, you'll see it's in polar mode. It doesn't say y equals, it says r equals, which is polar mode. And so I just typed in the answer that we just got. And so now when I go to hit graph, it gives me the ellipse. So kind of neat. So certainly we could use tools for those things. Just as a side note, one of the couple things I could kind of figure out on this. So this was the same graph. So if I look at the same graph, we could have sketched this probably pretty decently on our own without using the calculator. They told us where the directrix was. They said the eccentricity was 0.6, which is the same thing as 3 over 5. So in other words, there is a 3 to 5 relationship between a point on this graph. So they told us that, remember they said that the focus was at the pole. So I knew my focus was at 0, 0. So if there's supposed to be this 3 to 5 relationship right here, this is obviously a distance of 3, right? Well, 3/5 of 3 would tell me where to put that vertex. So that would give me a pretty good indication of, where to put all three of those pieces of info. As far as getting some of the other points on the graph, well, this would mainly be sort of a rough sketch. We could certainly, once we get our answer, we could certainly plug in some numbers to get some points. But we could at least get even a decent sketch just with the given information and knowing that it's an ellipse. So let me go through some other of these guys real quick. So the second one they gave us, they said the eccentricity was 1. So this is B from up above. So if my eccentricity is 1, remember that tells us that it's a parabola. They also said that the directrix is x equals -3. So you'll notice on this one, if x equals -3, in just a general, super simple sketch here. So if my x equals -3, then I know my directrix looks like this. So there's my directrix, which tells me if my focus is at the pole, as they say, then I know my parabola is going to open up to the right. And remember, in a parabola, your vertex is equidistant to those two values. So if this is at 0 and this is at -3, I know my vertex is at -1.5. All right, so I know I'm going to get something looking like this if I were to graph it. So a lot of information we can pull out of what they're giving us. Because it's opening to the right, two things we want to note. I'm using the formula that was said 1 minus, not 1 plus. I'm using now 1 minus because it goes to the right. I'm also using cosine because cosine will go with anything that goes left or right. From there, we're just plugging in the numbers. Again, we're using the directrix. They said x equals -3. We're always using that as a positive. We're not putting in a negative for that guy. And so that's why in the formulas you'll notice that it said for this one, it said x equals -k. So the opposite of k. So we're using +3 on this. Again, just plugging in the numbers. And then just simplifying it, and that's it. So again, I was able to come up with a decent sketch of this graph, certainly without a calculator or anything like that, but you could also take advantage of some graphing tools as long as they are in polar form, and you can still graph these, right, using those. So here's what this one would look like if you actually did it correctly within a calculator. All right, let's go to the third one. So on the third one, they said the eccentricity was 4/3. You'll notice that's greater than 1. So this guy has to be the hyperbola. Let me abbreviate that. So we know it's a hyperbola. On this one, it says, they said up above that the directrix, I'm just going to write it right here so you can see it, but they said the directrix was y equals 3. So as soon as I see that it's a y equals, I now know that this is a graph that will open up or down because they are giving me a horizontal directrix. And my graph always goes away from the directrix. So this guy will open up and down. So that tells me as far as which formula I should use. So let's look back at this together. So keep this in mind, y equals 3. So if I look back at our formulas page, so as I look at these guys, because y equals 3, +3, I know I'm going to use this formula right here. So we got the KE 1 plus E sine theta. Oh, there we go. I was like, where was I going to write this? So it should look like that. So let's go ahead and sub in the information they gave us. So R equals, so in this case we know the K value was 3, so we're putting a 3 in there. Let's say KE, so my E value was 4/3. That will simplify nicely for us as those 3's will cancel. On bottom we have 1 plus E sine theta, so 1 plus, again that E value was 4/3. Sine theta, and that's really the answer, but they do like us to kind of clean that up. So obviously on top I can clean that up to just be a 4. On this one, let me do it over here because I'm kind of running low on room. I can't write that small. So on top, if I have my 4, and on bottom I'm looking at that 1 plus 4/3 sine theta. So it comes out looking like that. They will do an extra simplifying here. Instead of leaving a fraction within the fraction, they'll multiply top and bottom by 3. Which I'm not going to say that's kind of right or wrong to do. It's just a way of kind of not having a complex fraction. We don't really want to have fractions within fractions, so I guess it's a fairly appropriate move. Multiply top and bottom by 3. So it comes out looking like this. So let's kind of establish that as a good general rule of thumb to do, and we'll simplify it like they do. So do that within our assignments as well. Okay, so there's our process of doing that. Let me flip. All right, so in these cases, they're now giving us these equations, and we're kind of working backwards. We're going to determine the eccentricity, what conic it is, and then what the directrix is. If you look back at the sort of the raw form of these formulas, remember on bottom, this always said 1 plus or minus e cosine theta, right? So essentially, I want to divide by whatever this number is, the constant, so that I can get it back to that raw form of a value of 1 right there, and then I'll be able to identify kind of what's what within that setup. So they said, let's divide all this by 3 so that that can be a 1, and they gave it this look right here. So they said it becomes that look right there. And now I can get a little more out of this. Remember, the formula is this represents KE, and this guy was our value for E. So I can now tell that E is 2. So there's my eccentricity. Obviously, that's a value greater than 1, so we know it's a hyperbola. I can also now look at this and say, well, if 3 equals KE, and my E value is 2, then I can divide over that 2 and figure out that my K value is 1.5, right? 3 over 2, 1.5. So once you kind of get it into this form, it's really easy to pull out the information that we would need on this. And so as far as the directrix goes, do keep in mind that this is a hyperbola that is opening left and right because there's a cosine here. We always know the directrix is like y equals k. So in this case, if my k value is 1.5, then my directrix is, sorry, I should say x equals my k value if it's going to open left or right. So my directrix would be x equals 1.5. As far as just making sure we get the signs right, let me just quickly remind you that when this was positive, this was positive. When this is minus, this is a minus, right? So we can always kind of see that relationship too. So I knew to write this as x equals, I should look at this one. I knew to write this as x equals positive 1.5 because in the setup there's a plus right here. So these guys always go hand in hand. All right. So let's do one of those together on our own. Let me just mention this, give you one more thing to look at here. So again, the process on this would be, let's divide everything by 5 so that this can be 1 minus e sine theta, and then we pull out the information from there. So if I divide this by 5, it's going to become 2/5. Obviously, 2/5 is the e value, the eccentricity, and because that is less than 1, that tells me that this would have to be an ellipse. Okay, and so that's how we would identify the ellipse. That is also how we identify the eccentricity of it. If this is KE, after you divide it by 5, it's going to be a 3, right? So if I set 3 equal to KE, I can solve for my K value. Because this is a sine function, I know that my directrix is going to be y equals something. And in this case, because it's minus, I know it's going to be y equals negative k, and so that's where they got this statement right here. So let's do one of these together so we can take a look at it. So again, the first thing we would look at is the constant, which is a 6. I want this to be a 1, so we divide everything by 6, and it becomes that look right there. So right off the bat, the first thing we can tell is my eccentricity is 1, because there's no other value there. That also tells me that it is a parabola. And I can see by this that this is a parabola that is opening to the left. because that's a plus and that's a cosine. And so based on that, I know it's going to open to the left. So remember, when you see a positive cosine, that was this one right here. So it's going to be opening to the left because it always goes away from the directrix. As far as getting the value for K and the equation of the directrix, remember this equals KE. So if I just said 2 equals KE, and if E equals 1, then K must equal 2. So that's my K value. As far as the equation of the directrix, if this is opening left or right, I know that my directrix needs to be the equation x equals something. And if this is positive, then x equals positive K is the equation of our directrix. So those are kind of the 4 things that we should be able to pull out of those equations. All right, let me jump down to this section down here. So this is one now where they're just saying, hey, okay, we're going to give you this equation, r equals 6 over 2 plus sine theta, and they're just saying basically analyze it. So what's all the information we could pull out of that? Not only the eccentricity, but they also want us to identify like A, B, and C. And so I wanted to remind you real quick what A, B, and C represented all along this chapter. So far this chapter, A is always going to represent the distance from the center to a vertex. So wherever, like, I'll just use this graph as an example. So if my center is here, so the distance from this center to either vertex, either that one or from here to here, is our value for A. Our value for B has been along the minor axis, right, on something like this. It's like the short distance to a what we call maybe a covertex or something like that. So from the center to a covertex would be our value for B. And then C is always the distance from the center to the focus, right? So whatever my center is to my focus is going to be the value for C. And so that's been consistent all chapter long. So let's look at what they gave us here. So the first thing they're going to do is, just like we did up above, let's divide everything by 2 so that we can put this more in alignment with the raw formula in order to pull out the information that we want to see. So a couple things that we just talked about is we can see the eccentricity is 0.5. One of the things they want us to identify. And so because it's 0.5, that's a value less than 1, which must mean this is an ellipse. As far as this being a positive sine function, well, as soon as I see sine, I know this is an ellipse where the major axis is up and down. Right? This is an up and down graph. Right? This is kind of opening downward. This is opening upward. So, and we see the major axis is going to run right through the largest part of that graph. And so because it's a sine function, we can see that it's an ellipse where the focal axis or the major axis is running up and down. As far as the directrix on this, remember if my E is 0.5, then based on what we see here, and 3 equals KE, so 3 equals K times E, then we can figure out that K is 6. And it's got to be, because of this, and because of this, right, as we just talked about, it's got to be Y equals positive 6. And so we can get the directrix out of that. So all that is stuff that we had just talked about within those previous problems. So let's talk a little further about some more of this information here. So if you do peek at page 606, which is what we've already been looking at, we've seen the equations that we've already been looking at for these. All right, so let's peek at kind of this information right here. So we just determined that because this was a sine function and it's an ellipse, we know that the major axis, the focal axis, is vertical. One of the key things that they keep sticking with on this that we got to keep in mind is they're using the focus at the pole at 0, 0 as kind of a key point here. So we're kind of determining all this information from a graph with our focus being at the pole. And so that's important. So we have a one of our foci is right there. So we got to keep that in mind. Okay, so if that is my focus, and this is an ellipse with a vertical focal axis, then this vertex, the highest point, is going to be up here at pi over 2. Right, so just think of your circle for a minute, right? On like unit circle, this is, or any circle really, this is pi over 2, and down here the other one would be at 3 pi over 2. So that's where our two vertices would have to go. Think back to how we wrote an ordered pair in polar form. This was r, the radius, which is this guy, and this was the angle. It was like the y-coordinate. So as I look at this, as far as the vertices go, well, I now know the y-coordinates. We know theta, right? Pi over 2 and 3 pi over 2. So I know this guy and I know this guy. So how do we figure out that this is 2 and this is 6? Well, we can just plug those into our formula. So if I put pi over 2 right here and calculate this, the r value, which goes right here, comes out to be 2. And so that's where they got this point on the graph. If you plug in 3 pi over 2 for theta, and we simplify that, we come out with our r value of 6. And that's where they got this point right here. Remember that this represents a radius from 0, 0. So at pi over 2, I have a radius of 2. And at 3 pi over 2, I have a radius of 6. So that's 6 units right there. So we can now use that information to figure out where the center of this ellipse is located. So if that's 2 units up and that's 6 units down, I'm looking at a total of 8, right? So I want to go halfway in between. So 1, 2, 3, 4 would be the center of this ellipse. So my center is right there at, well, if I'm looking at this as like an XY grid, it's like at -2, right? So let's use that to determine these guys right here, A, B, and C. So now based on that, I can see that my distance from the center to a focus is 2 units. So there's my C value, should be 2. My distance from the center to a vertex is 4 units. And so that should be my A value. And as far as getting the B value, we're going back to our, well, it kind of looks like our Pythagorean theorem formula. They call it a Pythagorean relation, so it's not exactly the Pythagorean theorem formula, but it's obviously connected to it. So I'm using my A squared minus C squared in order to figure out what B is, right? And so that's where they came up with the B value. So you just have to remember what A, B, and C represent, so that once you start looking at this information, we're able to identify what those values are really by looking at that graph. All right. As far as this stuff goes, we already identified that by looking at this graph. So I do think sketching the graphs as you're getting that information will really help identify all the parts to this. Let me flip. Thought we should try one of those. So if you want to try one of those for practice, here we go. Let's go. I'll go through this as quickly as I can for you. And then we have one last thing to talk about. So first thing I'm going to do is divide all of this by 3. So it becomes 4 over 1 minus 2 cosine theta. Right off the bat, I can see that my eccentricity is a 2. Greater than 1, which tells me this is a hyperbola. And remember, they are putting a focus here at the pole. So there needs to be a focus point right there. If this is a cosine, I know that these guys are going to open left and right. So I should get this kind of a look right here, either my H looking like this or my Hurley sine H looking like this. And yes, the hyperbola does look like a Hurley sine, so if you take a look at that, that's where they got it. So anyway, remember that this equals KE. So if 4 equals KE, I also know that my K value is 2. I know that my directrix, remember, so if this is a cosine, then my directrix must be x equals my K value. And so if this is negative, then so is this. So x equals negative K. So if x equals negative 2, then I'm going to do this in red. Here's our directrix. And so for these guys, that means I'm going to get the hyperbola here and here. So it's going to look something like this. So do keep in mind that somewhere in there we have the center between those two curves, not necessarily on the directrix. Really what you're going to see in a hyperbola is you got a focus and directrix for each curve. So there's a scenario playing out over here. There's a similar scenario getting mirrored on this other side, but we really only need to look at sort of one half of this to get the important information. So the next thing we're going to have to do to go any further is to figure out what are the coordinates of that vertex right there and what are the coordinates of that vertex right there. I need to know those points in order to figure out where the center is, right? Because I need to know this guy because it's the distance from the center to the vertex that gives me my A value, and it's the distance from the center to the focus that gives me my C value. Okay, and so I need to know what he is in order to figure that out. So in order to get those 2 points right there, so do keep in mind this is like 0, 0. So I need to know what is this radius right here. And if you think of it in terms of like a circle, I'm going to travel from here to here is pi. So if I want I'll put them down here. If I want like coordinates for this, remember coordinates are written in polar form like this. So I'm going to plug in pi back up here into our formula in order to figure out the radius that's going to take me from 0, 0, which is right here, to that guy right there. And so if you did plug in pi in for this and simplify it, you will get 4/3 as that radius. The other one is a little trickier to find. So go with me on this for a minute. So I need to get essentially this radius right here. Right, so this is 0, 0. I need to know how far I'm traveling that direction. I'm not going to use pi in this because I just used that to get this 4/3. So instead what they're going to have you do on this, and there's a couple different approaches here, but they're going to have you use a value of 0 degrees or 0 radians in order to get this. Essentially what they're saying is if I were to go with my radius, if I were to go in the negative direction, I would be right there, and then from there I can go 0 degrees. I don't have to travel anywhere from there. I would be on that point. And so they're going to plug in 0 for this guy. So if I plug in 0 into theta right there, let's see, cosine of 0 is 1, so 1 minus 2 is negative 1. 4 divided by negative 1 is negative 4. Okay. So there's our 2 vertices, and so that's this guy. This was negative 4, 0, and this one right there is at 4/3 pi. Now do keep in mind, this is in terms of a radius and an angle that we traveled. So if I want to figure out sort of what's in the middle between those 2 points, if I was just looking sort of in a linear view here, then if this is 0, this is technically negative 4/3, and this is still negative 4. So I need to know what is the halfway point between negative 4/3 and negative 4. So basically add them up and divide by 2. And if you did that, you would get negative 8/3. So let me Let me just fill in a couple things here. So that's at -8/3. This guy was at -4. And this guy was at, again, it's technically -4/3. If we're going to write it in polar form, this was the appropriate way to write it because we're including the angle. But if I'm just looking at sort of a linear form because I need to deal with distances, then technically that's like -4/3 at that little point right there. So what does that tell us? So that tells us that the distance from the center to either focus is 8/3. So we can recognize now our C value is 8/3. How about our A value? So the distance for our A value goes from the center to the vertex. So if I just found the difference between those two numbers, I'm going to be looking at 4/3. And so that's kind of the process they want us to use to come up with that information. I have seen the book on some of the homework problems write these as potentially a negative value. I've never seen any other book do that because really these are supposed to represent just a distance in either direction, right? Because my A value can go from here to here, or it can go from here to here. So I would never write those as negatives, even though I have seen the back of the book use some negative answers for some of those values. Really, I don't see that as the appropriate way of writing those numbers. So I would always write them as a positive. In order to get our B value, so stick with me on this because there is one extra thing I want to show you on this. So in order to get our B value, remember that in a hyperbola, C squared equals A squared plus B squared. And so now I can say, let's see if I square that, so 64/9 equals 16/9 plus whatever B squared is. So if I subtract that over and then square root, let's see, 64 minus 16 would be 48. So 48/9, and then I would square root that. But realistically, I actually want it as B squared because we're going to be using this to finish this off by writing the Cartesian equation, which is like the general form like this that we were used to seeing with x and y. And so that's why we need to come up with B squared as 48/9. So, in light of what that hyperbola looks like, remember the general equation here. Is looking like this. And so that's why we had to come up with the center, we had to come up with our A squared, we had to come up with B squared. So all that information was needed in order to write this guy right here. So we can see that the center is at -8/3, 0. So there's the center. Let me just write it here. And so that's going to, this guy's going to go in for H, that guy's going to go in for K, and right here we had A squared, right here we had B squared. So I'm just going to sub in that information to get our final answer. Let's see, our A squared was 16/9. And 48/9. And there we go. Cartesian form of that answer. I wanted to go over one of the homework problems real quick. So if you do want to hang out for this one, you can follow along. So this is going to be number 21 from page 610 of our homework. So on this one here, let me show you the problem real quick. So this one says, find the polar equation for the ellipse, saying the focus is at the pole, like all these other ones have been. They are giving us polar coordinates for the endpoints of the major axis, right? And so remember, if this is an ellipse, right, the major axis, also known as the focal axis, it's the widest portion of that ellipse. And so these are the two endpoints that they're giving us. In other words, those are the two vertices, right? If they're the endpoints, those are the vertices. And so I have some of that laid out for us already here. So we have a focus right there at 0, 0. They gave us the 1.50, and then if I went 6 and then pi, I would have this guy right here. Okay, and so they're giving us that information. So we can see on this one that if those are the two endpoints, if I add them up and divide by 2, I can see the center of this ellipse is at 2 1/4, and from that I can pull out all my values that we needed right here, right? So my C value is simply the distance from the center to a focus. And remember, our focus was right there at the pole at 0, 0. Our A value is the distance from the center to either vertex. So I just subtracted those to get the 3.75. My eccentricity, which should just be C over A, is going to be the 0.6. Since this one is obviously running mainly left and right, that's how I know to use the cosine formula. I'm using the plus because it is obviously shifted, the center has been shifted to the left of center, the left of 0, 0. So that's why we're using the 1 plus E, I should say 1 plus E cosine theta. Sorry, there should be an E right there. So we already figured out our value for E was 0.6. And so that's going to get subbed in for E. Once we know that, we're actually going to use this whole formula to solve for K, because we don't know what K is yet. Slide that up. So we're going to use one of the points that we knew that they gave us, and we're going to plug it into this formula in order to solve for K. So we're going to put our 0 in for theta and our R value in for R. So it's going to look like this. And of course we put in the 0.6 for E. And so now we just have to get K by itself. And if you get K by itself, you're going to come out with K is 4. And so now we can plug in the 4 for K. So here's really the main layout. We're just going to do a little cleanup on that. This was another case where they multiplied the top and the bottom by 5 so that you could get rid of the decimal inside the fraction. Comes out with a nice clean look like this. So hopefully that will help with some of the homework, but that is it for this one.